especially talking about the electrons. It's called electron configuration, and a lot of times students have had it in high school, but you probably haven't had it to the depth that you need to have it for general college, general chemistry in college. So I better snooze that. My computer's got a mind of its own today. So yeah, you told me that, I'll go clear down to here. These are actually, and I have a little song to go along with this here in a minute, but these are what, 5 different versions of what an atom looks like. Of course, all matter is made up of atoms. You told me the electrons, these little buzzy things, are actually the electrons. So this is the most modern version of an atom. So what's in the center of an atom? The nucleus, protons, and neutrons, exactly. We're going to talk about that. But starting here, back in 1803, Dalton proposed his, and he wasn't the first to say that all matter is made up of atoms. Actually, atoms is a way older term used back in the 200 BC by, I think it was Aristotle, I get my age stuff. But anyway, he wrote the Dalton's atomic theory. And actually, we talked about Dalton's atomic theory earlier. But then it wasn't until 1904, you see the difference between these two, is that instead of just an atom being a blob, here what Thomson discovered was that there are positively and negatively charged little pieces that make up an atom. This is called the plum pudding model, though, because he didn't have it like we know it today, where the electrons are outside and the protons. He didn't have the idea of neutrons. Then finally, in 1911, Rutherford, then, you can kind of see the dark purple and the light purple. Okay, so that light purple is where the electrons are. And so finally, we get the idea of a nucleus with Rutherford's model. Okay. And the difference between Rutherford and Bohr is that Bohr said, all right, the electrons are outside the nucleus, but, and we're going to spend some time talking about this, and again, this is where sometimes students' eyes glaze over, because you visited this idea where electrons actually are in orbitals. Electrons are not all created equally. Okay, electrons are closer to the nucleus with lower energy, or farther from the nucleus with higher energy. And so Bohr actually did that. And then Schrodinger, you think of Schrodinger's cat, right? Physics. Schrodinger actually then did a math here to decide to more pin down where the electrons are using calculus. So here is my, and I apologize in advance if it's just too way catchy. So that was just an exercise in creativity. So Thomson, in his plum pudding model, he kind of said that he knew there were positively charged and negatively charged pieces to an atom, but he just kind of put them as coexisting in the little orb that Dalton called. This is more what we know today, obviously. You guys told me nucleus, protons and neutrons, electrons outside the nucleus. If you read the caption here, it actually, this is not drawn to scale. It says electrons are too close to the nucleus. If the entire room were represented by 5 meters on all 3 sides, the nucleus would only be about the size of the period at the end of that page, which that's not a blown-up period, that's a regular period. Atoms are very small. I think we talked about that before. So atoms are very small, let alone the electrons around the nuclei of atoms. This is actually showing some like electron transitions here. So we have, each of these lines would be an energy level that an electron can reside at. Now we have this whole proximity of the electrons to the nucleus, but also we have with regard to energy level. So again, the closer it is, the lower the energy, the farther away from the nucleus it is, the higher the energy. These would be transitions. These would be, like it says, exciting electrons up from lower states upward. Okay, these then are transitions downward. Hopefully you can see the 2 colors. We have a red color here and a blue color here. Actually, those would be the relative colors maybe that light would be emitted as electrons fall from an excited state back down to a ground state. Which transition is bigger? Which leap is bigger, the R or the B? Which one has to fall more? The B is falling more. Actually, as it turns out, blue, being blue, is a higher energy than red otherwise. This is actually how fireworks work. So what they do is they take an assortment of metals, and the electrons are, and it's delay, right? So you have to get them up into the sky, and then I don't know how they work, but you get them up in the sky, and then you take the atoms of those elements and you excite those electrons. And as they fall down, they emit that characteristic light. So fireworks have come a long way, okay? But that characteristic light that they emit, because now they got more colors than they used to be, is actually a function of that transition. It's called. So the Bohr actually was the first person to go ahead and say electrons aren't all created equally. You can see kind of these different energy levels associated with the nucleus and electrons at these various energy levels. But what we're going to see is those energy levels are broken up more into subshells. I have another little video to show you. So it reminds me of Christmas, like the whole red and green thing. Okay, of course the red and green represent the two subatomic particles in the nucleus, which is protons and neutrons. And then that fuzz outside there are the electrons. The denser, that kind of makes me feel like bugs or something, the denser the look of that, the more likely electrons are to be in that region. So with Bohr, actually, we've already kind of seen nucleus, energy level, increasing energy level. So we have this idea of these energy levels. Energy levels are quantized. If you want to put a little star here, a lot of times this makes it, bless you, to my vocabulary. Bless you. Your star might not be more as much description as just vocab. So it's vocab. Okay, quantized. If you think of the word quantized, hopefully you kind of think of quantity. And in this case, with electrons, we're talking about quantity of energy. So quantized value is, I've done this a few years, so it's like I stand up here and I keep putting my hands up like that. So all I'm doing, when I think of energy levels associated with electrons, is this is going to be an energy diagram, and this is going to be increasing energy as you go up, increase in energy, okay? And then, so we kind of have these different energy levels here, here. So it's quantized. It can't be in between. So to kind of show that, I've got these two not drawn to scale. Can you imagine climbing at steps that is about up to here in your waist? You're crawling up, right? It reminds me of like the Incredible Shrinking Man. So I don't know. But after you get over that kind of shock, think of this chemist. This chemist can be at this elevation, this elevation, this elevation, or he or she, I guess he, can go down. Okay, so this actually on the stairs is showing the kind of the quantized possibilities for elevation for that chemist. This is more how electrons are. Okay, this, the energy associated with electrons are. This is not. This would be continuous versus quantized. So we've already kind of talked about exciting electrons to a higher energy level. When we get rolling here next week, it's what's called finding homes for electrons. We're going to find homes for electrons as those electrons are in their most chillaxed ground state. So the lowest allowed energy state for a set of electrons. So I kind of call them couch potatoes, like they're just as chillaxed as they can be. No energy. Watching the fire. Okay. The most stable situation. In fireworks, what happens, like I was telling you, is for the metals, the metal atoms are energized and the electrons are excited to a higher energy level by something else. The light we see is as those electrons fall down. So excited states can only be attained by putting energy in. They're endothermic. Okay, and as an electron falls from excited state down to a ground state or lower state, then energy is released. So excited states. So excited states in general are states that are, there's a lot of things that happen in our world with regard to chemistry, being kind of unstable. Unstable states are just itching to become stable. And that's kind of what we see as electrons transition down from an excited state to a ground state. All right, so the video and the figure that we saw with the nucleus and the okay, that's the region of space where you can expect to find an electron. That's what we call the electron orbital. Also associated with location is energy. So we have energy and location kind of go together with a particular orbital. So as you see those kind of things that make the itch, okay, now electrons can be either here, 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 okay. Like I told you before, kind of the denser the looking kind of dots, then the more likely they are to be in that location. Generally speaking, those regions are 95% of the time an electron will be in the regions that we're specifying here. Okay. Trying to decide how do I want to describe this. Electrons are located in orbitals. I'm going to go ahead, anytime it's okay with you, you see the word orbital, we know that's a region of space, but I want you to think box. An orbital is a box. Okay. So orbital is a box. My boxes get really sloppy sometimes, okay? So it's a place we can find electrons as we get to draw them. And this says that there's a maximum of 2 electrons that can be placed in any orbital. And if you put 2 electrons, and I'm going to put 2 electrons in this one little orbital I have up here, they have to have opposite spins. Now, as some of you may already know, we use arrows to represent electrons. So here I go. There's my orbital. I'm going to put 2 electrons, so that arrow is 1 electron, to show its opposite spins, and we'll be talking about this quantum number, m sub s, probably next week. To show my second one that has a different spin, if it's a visual sort of thing, I'm going to show it as an arrow downward in that same box. Okay, so electrons or arrows.
Most people, I look like most people, but on the inside, I feel chronic white.
Okay, I thought it was going to make me do that. I didn't stop my YouTube video. So these boxes or orbitals are grouped into subshells, and I think if it's okay with you, again, this is where your eyes start to glaze over. Like, oh, I did this in high school chemistry. Well, just hold on to that thought and work with that and fit it into college chemistry, and you'll do great. I worry about this. So there are different orbital types. There, as some of you guys know, there's an S type, and it has 1 box, 1 orbital. There's a P type, and it has 3 orbitals. D type, 5 orbitals. See how my box is starting to get sloppy? Darn it. And then the most sophisticated type of orbital, which has 7 orbitals, that we need to worry about as electrons are all in their ground state, is the F type. That's it. I put 2 electrons in each, so you can kind of start to see those in your own imagination, those little electrons. So this says orbitals are grouped according to subshells, with each orbital in the subshell having exactly the same energy. So that last thing in italics, now this is kind of weird, but I'm going to go ahead and put an energy diagram here, okay? So all this is saying is that these 3 have the same energy, these 5 have the same energy as I've drawn them, and these 7 have the same energy. Now, kind of as I've drawn them over there, you're never going to see kind of that sort of deal with regard to a real situation with electrons. But I think it works. Subshells of orbitals are found in different energy levels. So I'm kind of going back and forth here. And we'll be building on this next week. I was like, I couldn't remember how many slides there was for this first part. I'm like, so do we finish? There's 60 slides in this. Like that, okay, no homework today, so we're doing 60 slides. So I want to go ahead over here, though, and you're just going to have to remember this for next week, is I want to start kind of talking, I call it the onion. Subshells of orbitals are found in different, what we call principal energy levels. So I kind of gave myself a little more room here. I'm going to go n is equal to 1. That is my principal energy level. N is equal to, n is my principal energy level. This one happens to be 1. Let me go ahead and show you that actually when n is equal to 1, I have one subshell, the lowest of the sophistication here. I have a 1s subshell, and it follows that pattern. I just have one box. When n is equal to 2, I get a pickup. I have a 2s with one box, and I have the next one. 2p with, guess what, 3 boxes. 3 orbitals. When n is equal to 3, I'm going to have to, I guess it'll probably be next week, might even be the following week, kind of show you how I'm a little bit lying here, but just go with me, I'll try to fix it later. N is equal to 3, we of course have the 3s, we have the 3p, and now we get to, guess what, pick up the 3d. So if I was going to draw those boxes, it would look like this, 1, 3, and 5. I'm going to do one more when n is equal to 4. And you guessed it, I get a 4s, a 4p, a 4d, and now finally, this is the first principal energy level, I get the f. So excited to get 4f. So let me go ahead and draw these in right quick. Every D type has 5 boxes, every F type has, oh my goodness gracious, those are 7. Woo! All right. Cool. I call it the onion. Lowest energy, highest energy. Again, this isn't exactly right, but it'll kind of get us down the road to what I'm going to talk about today. I'm going to show you this video because I was like, how do I describe Heisenberg's uncertainty principle? Heisenberg was one of the names of the men we saw in the video we watched about the history of the atom. But generally what you're hopefully going to see is that when I talk about electrons being at an energy and electrons having a particular location, you can't know both. For any given electron, you can't know both its energy and its location at the same time. So let's see, this is a TED Talk, it's kind of fun. What our takeaway from this, well, I was trying to think now, what impact does the Heisenberg's uncertainty principle have on us for Unit 4? And I guess to me, it kind of goes back to what Schrodinger, who did the whole wave function of the electron particle as it's associated with an atom. When he says where are electrons, he kind of does the dot, dot, dot. So Heisenberg's uncertainty principle is the dot, 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 kind of generally where electrons are. So back to something we can more sink our teeth into. I'm going to go ahead over here on this diagram. I am just for kicks going to go ahead and put an electron, where should I? I'll just put an electron here. I'll go ahead and make it an up electron. So one of the goals in this class is to ultimately be able to look at an electron and give it a set of quantum numbers, a zip code. For that electron, and I think I'll go ahead and do it, we actually would have, you know how you have like ordered pairs, X, Y, and Z if you have a third dimension. We're actually going to have 3 things here. We're going to have N, which you see N there. We're going to have a value for L. That's our subshell type. These are different L's. We're going to have values for M sub L, and don't think I'll get to that today. And then the last value is this, what we call the spin number, M sub S. So these are 4 quantities that we'll get to probably Monday that we can actually look at an electron and give it a zip code. So just for kicks, and this will make later, I'm going to go ahead and give the zip code for this one. So of course n is 1, so I'll do 1 comma. The L goes with the S value. For whatever reason, and this drives me nuts a little bit, I'll go ahead and write L values over here. The L value for S is 0, for P is 1, for D is 2, for F is 3. Ah, great. So now I know I'm going to put a 0 here. Then I need M sub L, and we'll talk more about that, but actually, as it turns out, that's also 0. My last one is my favorite one, M sub S. It's only got 2 possibilities. It's plus 1/2 or minus 1/2. Guess what? It just has to do whether it's an up arrow or down arrow. So I'm going to call that a plus 1/2. So those are the 4 kind of ordered pair numbers that say what that electron is. It's a zip code. It totally is a zip code. And you'll be zipping through those zip codes maybe by the end of the day, Monday. Okay. So the 4 things to say what the zip code of an electron is its principal energy level. L is its angular momentum quantum number, which is the S, P, D, and F. This is L over here. It's really not that complicated, but it does take it a bit further than probably you've covered in high school. The M sub L is the magnetic quantum number. I'll go ahead and do that over here too, if that's okay with you. I'm going to take these out and write underneath my kind of, at times, ugly looking boxes. And again, I'm getting a little ahead of myself, but I never know how's best to teach this. So I'm going to I'm going to put an M sub L under here. I'm going to go 0. I need 3 M sub L values here because I have 3 orbitals. I have M sub L value of -1, 0, and +1. Here, M sub L, I need 5 values. Guess what? Well, let's do it this way. It centers on 0, and on either side, I have a -2, -1, and I have a +1, +2. For the F-type subshell, I need 7 M sub L values. I'll go ahead and find my middle one. I'll put a 0 here, and then it kind of spreads out. So I'll go this way. +1, +2, +3, and then I'll go back. -1, -2, -3. So there you go. That's the M sub L value. That's it. And I already told you the most exciting one is the spin, which only has 2 possibilities because you can only have 2 electrons. Although you do have a homework where you can, what if you could put 3 electrons in each orbital? What would that look like? So M sub S, I'll do it this way. This up is +1/2, and this down is -1/2. Now, as we cover in chemistry, it's a lot cooler than just a little bit as I'm covering chemistry. There's a lot more an intersection between chemistry and physics. Okay? But it's still pretty cool. Okay, so N, the principal quantum number. N. Again, you had chemistry before, you've already kind of been talking about this. These are our principal energy levels. There are rules that go along with each of these numbers. So what does this symbol mean over here? What's that last symbol there? Infinity, yep. So honestly, I run out of room on this whiteboard. I could put n is equal to 105, n is equal to 1,000,000, n is equal to... Now granted, as I'm doing these higher ends, will electrons ever be at those principal energy levels in their ground state? No. Could you excite an electron up there? Yeah, theoretically, yes. Okay, so that's the rules for the principal energy level n. And like we've been talking, the higher the n, the higher the energy, and the further away the electron that is in that principal energy level, the farther it is from the nucleus, in general. So finally, this is our first, I think, that slide with the little colored open stacks around it. The highest value of n. Now, I talked about vocabulary, and we'll be talking more about this, but I'm going to underline valence shell. So as we find homes for electrons, the most important electrons are going to be our valence electrons. Valence shell, I'm going to say home, sweet home, home to valence. My electron is just like an E with a superscript negative sign. The valence shell, where the orbital or subshell where electrons are hanging out, has our valence electrons in it. Oh, in italics, this is identified, or this actually coincides with the period that the element is in. So we talked about the periodic table, we talked about groups and periods, and this periodic table, of course, is consistent with the black and white one you get for your tests. So, of course, the period is written over here. So if I was going to randomly pick on phosphorus, what period is phosphorus in? Yep, so phosphorus is period 3. Oh, it's so clear. So, actually, when we start to talk about, let's see, phosphorus, what's phosphorus's atomic number? Can't read it. Oh, 14, no, 15. Yeah, 15. So atomic number 15, that's the number of protons, right? 15 protons. If it's neutral, it has 15 electrons. So when we look at the valence electrons, the special of the 15, only some of them are special. The special ones are going to be here. These are going to be our valence. That's it. So. All right, L, angular momentum quantum number. And I already kind of told you this. Well, I tell you this. But possible values of L are limited by N. Oh my gosh. So N limits the values of L. So if we say, let's go up to 4. N is equal to 4. So if we go ahead in this relationship, plug a 4 in for N, 4 minus 1 is 3. So that means values of L could be 0, 1, 2, and 3. There we go. Values of L. That's an L. 0, 1, 2, 3. 0 for S, 1 for P, 2 for D, and 3 for F. If we pick 3, principal energy level N is equal to 3. Possible values, it's limited, L values are limited by N. So 3 minus 1 is 2, so it can only go 0, 1, and 2. 0, 1, 2. When L is equal to 2, when N is equal to 2, 2 minus 1 is 1, so you only got 0 and 1. When N is equal to 1, 1 minus 1 is 0, so it stops at 0. So that's how the principal energy level actually limits the, what I call kind of subshell types, values, possible values for L. These rules we talk about in chemistry are the rules he was talking about Heisenberg uncertainty principle, but it's the rules that are established by this universe. You want to change universes? As far as I'm concerned, you can rewrite the rules. Okay. So I just think it's so cool. So this, like I said, a lot of times in high school or in another chemistry class, you've talked about the S, P, D, and F. But now you're going to want to, for zip code purposes, go ahead and connect them with M sub L values of 0, 1, 2, and 3 respectively. So this, I kind of got ahead of myself. There's the first 4. Now, if you take an electron and excite it, it's possible that you're going to be interacting with these other subshell types. Then an M sub L value of 4 corresponds to an G type subshell. Personally, I've never had much use for it, but excited electrons can be there. And what did we say? Let's see. We said that n can go to infinity. So if n can go to infinity with regard to places to put excited electrons, then m sub L values, or L values, I should say L values, not m sub L values, L values can go to infinity minus 1. Anyway, so this says that the reason I stop here is that as we, in the next week, go ahead and find holes for electrons, we aren't going to have to go any higher than an L is equal to 3 value. So this actually oftentimes, let's see, this to me goes on to the next slide. The next slide a lot of times is also a vocabulary word. So we have these subshells of orbitals. Subshells of orbitals. A subshell of orbitals. Okay? So as it works out, if you were to pick any line here, as I've drawn it, these boxes, these orbitals in that line would be degenerate orbitals. These orbitals would be degenerate orbitals. So actually you have a homework also, like I said, it's fresh in my mind, less than, well, a little more than 12 hours ago. For instance, these, 5 orbitals and 3D, if both the n and the L value is the same, then the orbitals are degenerate. Which sounds negative, but it could be a positive thing. So as I've been doing this, okay, I kind of already got a little ahead of myself. This 1s, the n is 1 and the L is 0. If we go to n is equal to 2, we got 2 subshells. We have the 2s and the 2p. The n value for both of them is 2. The L value is 0 and 1, respectively. This is kind of going down, increasing energy. For n is equal to 3, we've got 3 different subshells. The 3s, 3p, 3d, n is all 3. In this case, for 3s, L is 0. For 3p, L is 1. For 3d, L is 2, etc. So that actually are the first 2 numbers in 4 numbers to show the quantum zip code. So you've got homework where you're going to do the n value, the L value, which is SPDF, the m sub L value, which is those I read out one in the box, and the m sub S value, which is just plus or minus 1/2. So those are the first 2 numbers in the quantum number. Well, that's as far as I wanted to get, because this is a good kind of break in the spot. Hopefully remember all that. I'm going to grab a quick snapshot so I don't forget it, and I'll put it out on Twitter. So nothing due on Monday, but we'll pick up here with our 60-slide card on today. And if you have questions, this could be a chemistry sort of weekend where you're getting ready for your unit exam on Thursday. Questions about like your lab. So yeah, you guys got it last time. So do your lab calculations, which I encourage you to do so I don't have to grade your semi-formal lab work. No cuts.